Okay, so today what we're going to do is we're going to essentially finish this sort of basic review of basic point set topology, right? So this is because as of now, I've mostly focused on talking about, well, algebra on complex numbers and talking a little bit about complex functions. And I talked about continuity and differentiability at a point, but I never really talked about a function being continuous or differentiable in a set and what that means, except for the case of power series in which we saw when is it that it was, right? We were able to show that a function is continuous or differentiable at a certain set, right? In particular, inside the radius of convergence. But we didn't really consider, say, a function that's continuous in a certain region or a certain set. And to do this, it's good to revisit some basics of point set topology before we do that. Okay, so that's what we're going to do for the rest of today, and then we'll we'll go back to talking about functions on Tuesday, right? And we'll start viewing functions as mappings from the complex number to complex numbers, and we'll spend a week, maybe a week and a half, studying what does this mapping do to the geometry? What do these mappings do to the geometry of the complex numbers, right? You can now ask questions like, if I have a circle and I take a map from the complex numbers to the complex numbers, what will this circle be transformed in, provided we know things about the function, right? Or lines, or crosses, or anything like this. And this tells us is going to tell us a lot about properties of the function, and is going to tell us, we're going to realize that we can actually say a lot about the geometry before we apply the function, and the geometry, and related to the geometry after we apply the function, is going to allow us to move understanding of geometry from one place to the other, right? In the so-called, by using so-called conformal mappings and so on. We'll talk about all of this, okay? But so today what we're going to do is just, I'll show you some very, very nice proofs in point set topology. Just, I assume that you'll either have seen or will see versions of this in other courses, but some of these proofs are so nice that is just worth seeing them another time. Okay, so we talked about open sets and closed sets, right? An open set was a set such that, or I should start, the neighborhood of a point is a set that for which you can draw a ball around the point and is still inside the set. And an open set is just a set that's a neighborhood for all the points, right? So again, S is open. Maybe it's worth just stating that again, because this is the most important thing. S is open if for all x in S, there exists delta such that the ball, right, where the ball, if you think in complex numbers, is just the ball, you draw a circle. In the general metric space are just all the points at a distance smaller or some smaller than something, right? This is inside S. Okay, right, so this is important because it'll be the best place to define functions, right? Because if you define a function here, you know that you can take limits to x, right? Because you just zoom in enough, right? If you define a function in S, then it will always make sense to talk about limits and derivatives and things like this in X, because all you have to do is you zoom in enough so that you have a ball, and then you can take limits from any direction and so on, right? This is what's crucial. Oh, I just saw that someone said the audio isn't good. Where is it not good? In Zoom or in? I should try to fix it. Okay. In Zoom there was a problem. I fixed it now, so Zoom should be good. Is the YouTube audio good? Perfect. All right. Thanks so much. Thanks for letting me know. Yeah, I had the microphone for the Zoom be another webcam that's far away in the office, so that explains it. But now it should be fixed. All right. Thanks. Appreciate it. Okay. So now there's two more properties. In fact, there'll be, I guess, three properties that will be very important of the regions in which we want to define functions, right? But I guess the third one we won't talk about until we talk about integration later on, maybe 2 weeks from now, a week and a half. For now, there's two properties that's much easier to understand why they're important, and one is connectedness, right? So connected. Right, so we want S. We want to understand when is it that a set S is connected, right? So we have an intuitive reasoning of what it means for a set to be connected, right? But the nice thing of point set topology is that oftentimes you come up with definitions. They don't feel like what you intuitively think would be the right definition. However, they turn out to be much, much nicer to work with, and you simply prove that it's equivalent to what you would intuitively think the definition is, right? But just intuitively speaking, right, this set should be not connected, right? Because I can't go, right? It's clearly split in two, right? At least in a complex plane, while this set should be connected. Right, this is the intuition. But now I'll give you, a point set topology style definition that's quite nice. Okay. To give you a little hint of what's to come, one thing that'll be very important in complex integration will be if instead of this set, I take one where there's a hole in the middle. Right? Then this set is still connected, right? I can still reach everywhere. However, it somehow has a hole in the middle, and this will be different. And it turns out that whether things have holes in the middle or not will be crucial later on. But for now, let's not worry about this and just talk about connected. So it turns out that, a very nice definition of connectedness. Set is connected if and only if there exists A and B open. So A and B open sets that partition S, right? Such that A union with B is S, and A intersected with B is nothing. Okay, so they partition S. Okay, and so now this is something I don't want to get into very much, but if right, so by open here, what I mean is that they're open in the topology in S, right? So if I think of S as my entire space, right, then I can define open sets there and so on. If I think S itself as a subset, then the relative topology is just a set is open if it's an open set on the large set, right? If S is inside some set E, then open sets in S are simply open sets in E restricted to S. Okay, so let's say, okay, so let's prove a simple proposition. Okay, so this feels like a bit of a strange definition, perhaps. Right, but already here you maybe can see that this at least corresponds to our intuition, right? Because this set is not connected, and indeed I can find two open sets. I just draw this open ball and this one. They don't intersect each other, and their union is S, or their union after you intersect with right? Their union after you intersect with the set S. Okay. I made the definition the other way around, of course, is if and only if there doesn't exist A and B open such that this holds. Yeah, sorry. Okay, let's see if there's another question. You need to require that A and B are non-empty, right? So if they're empty, then their intersection is empty. Okay. Yeah, sorry, I forgot. Right. If they are, it is non-connected if such sets exist, right? If you can split in two, like you're doing here, then it's non-open. And in the connected set, you won't be able to split in two, and we'll see in a second. Okay, so simple proposition: intervals are connected. Okay, so in R, right? Okay, so let's take an interval I inside of R, an interval Okay, so proof. Let's take I inside of R an interval, and let's prove that it is connected, right? And so, yeah, you're right. Sorry, yeah, and then empty, of course. Yes. Okay, I put all the quantifiers. Okay, of course they should be in an empty. Otherwise, you just take A to be S and B to be empty. Yeah, and an empty. Okay, now it's okay. Yeah, sorry. They of course need to be in an empty. They need to be open in an empty. Otherwise, it's very easy to, right? You just split it by taking A to be S and B to be nothing. Right? Okay. If there's anything, please write on the chat, and the person helping me out can just go on voice and tell me, because I don't always. It's a bit hard for me to see the chat while I'm here. But if you just go on voice, I can hear. I have this loud. Okay. All right. So let's say that I is an interval. Okay, then let's go by contradiction, right? Let's say that it's not connected. So let's take A and B, right? And then empty. Okay, open, or such that A union with B is identity, right? And A intersected with B is identity, is the interval, and A intersected with B is empty. Okay, and they're open, right? Okay, so if I is not connected, then let's take this and let's prove a contradiction. Okay, so how do we find this? Okay, so take A1 in A, okay, and take B1 in B. Okay, and now let's say, without loss of generality, let's say that without loss of generality, A1 is smaller than B1. Okay. Then, okay, if it's the other way around, you just flip the, right? You just flip the, right, the name of A and the name of B. Okay. All right. So now let's see visually what the idea of the proof is going to be. Right. So there's some interval, right? And now we have some A1 here and some B1 here. Okay, now the idea is we're going to take M, the M point. Okay, so let's call it M1, the midpoint. Right, because we're over R, such a thing exists. Right, so we can definitely take the midpoint. Okay, now the idea is that this midpoint will have to be either in A or in B, but not in both. Right, because the union of A and B is equal to the interval, and the intersection is empty, right? So let's say that this is in A, right? And I'm going to call this A2 and this B2. And what I did is I created a smaller interval, right? The smaller 2 points that are closer together, where one is in A and another is in B. And the idea will be to do this again and again and again in a way that you're going to converge into a point and try to get a contradiction this way. Okay, but let me do this in properly. So take M1, the midpoint. So M1, so if M1 is in A, take A2 equals M1 and B2 equals B1. Right? If M1 is in B, then take B2 equals M1 and A2 equals A2, right? And do this and continue. Okay, so the distance between A1 and Bn is definitely going to go to 0. right? Because every time is going by a half, right? And it's not so hard to see, right? You can use, the fact that Cauchy sequences converge, the fact that monotone sequences converge. You can use many of these facts. That AN will converge and BN will converge, right? The sequences of numbers will converge as n goes to infinity, right? And they'll converge to some point. Okay, let me call it x. But the point is because, right, this is going to 0, this is in fact the same x. Right? They need to converge to the same x. Okay? But because, right, A and B are complement in S, and they're open, they're also closed. Right? A and B are also closed. Right? Because they're complement, right? The A is the complement of B, and B is the complement of A in the relative topology in S. Right? And so this means, right, if you have a sequence converging in a closed set, then the limit point needs also to be in the closed set. Right? There's a few different ways of seeing this. Okay, one way is, right, if it wasn't in the set, the things that are not in the set are open, and so you could make a ball around X where no element of AN would get inside that ball, and therefore you couldn't have converged to start with. Right? But the point is, since they're also closed, X needs to be both in A and X needs to be in B. And so we get a contradiction. Okay? And there's two ways of thinking about this, right? I mean, depending how you rather think. One is you take the definition this way, right, with respect to the relative topology, right? The topology induced on S, or you can just think of these as sets that live in the same space as E, and then you just need that the union contains S, right? This will be the same. Okay, let me take a look at the chat because I saw there was a lot of activity. Is there anything that I need to address? No? Okay. So I noticed a few of you wrote me privately, I think, when you meant to write to everyone. So yeah, keep this in mind, because then you sometimes write privately and then I can see. Okay, so in R, intervals are connected. Okay, fine. And it's also not hard to see that if something is connected, then it needs to be an interval, but I'm not going to do this because we don't have time to do everything in point set topology. I'm instead going to prove something more interesting about complex numbers. Or the topology of complex numbers is just the topology of the plane. Okay, so let me keep this here. Sorry for the buggy definition to start with. As soon as we're proving the theorem, we'd realize. Okay. Right. I mean, another way to think about connectedness is that, right, there's no subset that's not empty or everything that's both open and closed. Okay, so more interesting theorem. Okay, so this, what I'm doing today is like highlighting a few theorems in point set topology. If you've seen some of these, hopefully you enjoy the refreshment. If you haven't, you should really grab, point set topology book and revisit some of these. In a couple of hours, you'll do this, and there's very nice type of arguments that goes in. And in particular, in Alford's, in the reference we're using on this third chapter, we spend quite a few pages doing point set topology, so you can revisit it there. Okay, so now let's say, so on the plane, basically what I'm going to show is in the plane, right? So I'm purposely saying in the plane to not say if it's, could be R2, but it could also, of course, be the complex numbers. In the plane, and an empty open set, let's say, is connected if and only if every 2 points can be reached by a polygon line. Okay, so what do I mean by a polygon line, right? It's kind of obvious, right? Let's say I have a set like this, right? It's open. Okay, so the boundary is not part of the set, right? It's open. Oh, I should have done this, right? Okay, this sometimes is, right? But it's open. And now, if I grab 2 points, what I mean by connected by a polygon line is simply, you can go one line and then more, and then another, right? This would be a polygon line, right? A finite, a finite a curve with finite piecewise linear components, right? With a finite number of components and it's piecewise linear. Okay, but we don't have to define exactly what a polygon line is. It will be, right, it's exactly what you think it will be, and in the proof it will be clear what. Okay. All right. Okay, so let's prove this. Because this is a very it's a very good example of the type of arguments that goes on, right? Because how do you argue, right, that something is connected if it's like we could have defined connectedness in this way, right? Although this way we would have only defined connectedness for open sets, this could have brought up some issues. But how do you argue that things don't get the partition into open sets just if and only if they're connected by a polygon line? Right? It's not completely clear how to do this. And this is a great example of a very neat, like, point set topology type argument. Okay, so let A, all right, let's prove one side of this. Let A be open, okay, and connected on the plane. Right? I mean, before I was talking about the reals, now I'm talking about the plane. Open and connected. Okay? Now we're going to argue that every 2 points can be connected by a polygon line. Okay, so how do we do this? So let A, little a in A, be a point. I mean, there's no, right? Let A in A. Now, right, we have to construct somehow a partition of the set A. Right, and the neat trick is we're gonna set the partition by just splitting it between the points that can be reached by a polygon line and the points that cannot. Right, so let A1, right, be the set of points in A that can be reached right from little a by a polygon line, and A1 the ones, A2 the ones that can't. Okay? Okay, so because we're going to try and prove that these things need to be right, they need to be empty, but in particular A1 is not empty, right, because A is inside A1. Okay, okay, let's prove. Okay, first part of the proof, let X in A1. Okay, so we're going to prove that A1 is open, right? Because if we prove that both of them are open, then because A is connected, one of them needs to be empty. Therefore, A2 is empty, which means that A1 is everything, so everything can be reached by a polygon line. Okay, so let's take X in A1, right? I should maybe keep track of what the goals are, right? So goal, yeah, maybe, to follow the proof is easier maybe if I just keep goal. Okay, I'll write another color. Goal, show that A1 is open. Okay, so how do we achieve this goal? Let X in A1. Okay, because A, let's keep a picture. I try to keep a picture to give some intuition of what's going on in these arguments. Right, we have A here, and maybe this is A1, right? The sets, and maybe this is A. Right, this whole thing is A. Right, and A1 is the sets where you can reach with the polygon line. Right, the idea will be if we take a point X here, because A is open, I can make a ball inside of A. Right, so let X be in A1. This means because A1 is open, this means that there exists a delta such that Bx delta is contained in A. Okay. So, right, but now think about this set is in A, right? So, but now take any point in this ball, right? Take a point Y in this ball. Clearly, Y can also be reached by a polygon line because I just do whatever travel I did to get to X, and I just need to do an extra line from getting X to Y, right? There is, for any Y inside this ball, there is a line, right? Because 2 points in a ball, they're connected by a line. I mean, we're using properties of the plane here, right? For any Y in Bxy, there is a line connecting X and Y, all the line inside of A. So Y needs to be in A1, right? Because I just found a polygon line. I just use whatever I went to X, and then I go to Y, right? So in particular, what this means is that, okay, let me try not to mix the colors. Bx delta is inside A1, therefore A1 is open. Okay, so this goal is done. All right, now we have to prove, okay, so we're going to go here. Second goal, prove that A2 is also open. Okay, so if it's empty is open, that's not very interesting. So let's take a point X in A2. Okay, let's do the same thing because, right, now we are in A2. Let's say that this was A2. Now there is, again, let's say I have a point here. There is a ball that lies inside of A, right? So because A is open. So there exists delta bigger than 0 such that the ball X delta is inside of A. Okay, and what's going to be the argument is if in this ball you had a point that could be reached by a path from A, then you could just extend the path into X, and that's a contradiction, right? So if vector Y inside Bx delta was, if satisfied that it was in A1, then we could extend the line, right, the polygon line to X. So it must be that Y is not in A1, and therefore Y is in A2. So Bx delta is inside A2, so A2 is open. So this is done. Okay, but since I just split the set A, which was connected into two open sets, one of them needs disjoint open sets. One of them needs to be empty. Therefore, A2 is empty, right? Because A1 has A in it, so it can't be empty, right? So all this implies right? All this implies that A2 needs to be empty, right? Because I couldn't have, right? What was the part of the argument that was just not right? Is I can't start by taking a point in A2. Okay, so we proved one side of this implication. Okay. Now let's prove the other side. Okay, so let me keep the theorem and maybe erase the proof. Do the other one. The argument is, I mean, not the same, but the same style. Okay, so the other part of the proof, right? So if every 2 points can be reached by a polygon line, then the set is connected, right? So what we're going to prove, so proof, let's see how I wrote that. So an empty set is connected if and only if every 2 points can be reached by a polygon line. So I'm going to do the proof of this side. Okay, so let's say that every 2 points can be reached by a polygon line. Okay. Is there any question that I should address? I see the chat moving, but I can't. Okay. No? Okay. All right. If anything, just feel free to interrupt. Just unmute if anyone wants to ask a question. I'm very happy to be interrupted and have some participation. Okay. So, okay. So now I lost my train of thought. If every 2 points can be connected, then it needs to be. If every 2 points can be joined by a polygon line, then it needs to be connected. Okay. All right. So let's go by contradiction, right? Let's say that S was equal to A and B, right? Open and empty and non-intersecting. Okay. Now let's take A1 in A, or let's take an A, let's say A in A and B in B. Right? So because they're non-empty, these things must exist. But since they are connected by a polygon line, right, they must be connected. I shouldn't use the word connected. They are linked. Maybe it's a better, Otherwise, I'm using, it's not very good, a habit to use words that are also definite. They are linked by a polygon line. Okay, so what's the idea? Now take the line, right? There'll be some polygon line like this. There goes to B. Somewhere in this polygon line, there must be a switch from something in A to something in B, right? Somewhere, like an A1 in A and a B1 in B, right? There's a finite number of jumps. You start in A, you end in B. Somewhere you need to jump from A to B. You might jump from A to B, back to A, and so on, but there must exist a place in the polygon line where you jump from A to B. So let's say B1 be the first corner, or I'm going to call it vertex, say, or corner is okay, right? Corner of the polygon line, I of course mean these, right? The kings. First corner in B, and A and A1, the corner before that. Okay? I mean, I'm not being super careful in defining this, but it's clear what I mean here, right? Because I just take the first time I jump to B, and that's B1, and A1 is in A. Okay? Now just restrict, right, the interval, right? The line from A1 to B1, we know is connected. Right? Let's call this set L. Right? We just showed that intervals are connected, right? So this is connected. Okay? Right? However, if we were to look, L would be equal to, right? You could take, I guess, A intersected with L, right? Union B intersected with L. Right? And this would be because B1, right? This would be a contradiction. Why? Because, right, they are open. This partition would be, right, A intersected with L and B intersected with L are open, right, in the topology of L, in the relative topology of L, right? Or if we think of that definition where we might include supersets, right, then it's clear, right? Their intersection is, of course, empty, right? And they are non-empty, right? Because A1 is inside A intersected with L, and B1 is inside B intersected with L, right? And so this is a contradiction, right? Because basically what we showed is that, right, if S is not, right, if S wasn't connected, if this MBN existed, then there would be a way to partition, right, with open sets the line, and we know that it isn't the case because we just showed that, right? And so this must mean that indeed, right, there's something wrong. S is connected. Right, there's ways to avoid the need to apply the argument of contradiction if this is something that you prefer. But okay, this makes it quite clear, I think. Okay, so now the other definition that's very important is of a compact set. Okay, but I just wanted to show these for you to see the kinds of arguments that go into topology. And the nice thing is that, you know, we here define everything with respect to balls and with respect to a metric space, right? We had this notion that if we had a point, an open set should be one where if I zoom enough, I have all the points that are near that one, right? But in order to do this, I need a notion of near, right? The distance. I need to be in a metric space. But actually, you can do point set topology without any notion of distance. You can do point set topology by just defining a universe, a set where you're going to define the topology, and then just you define which of their subsets are the open sets, and they need to satisfy certain axiomatic rules, like unions of any amount of open sets needs to be an open set, and so on and so forth. And then you can basically, if you trace back at what we did in all these proofs, essentially, all we use in the proofs, almost all the ones in the book in that chapter, they only use those properties about open sets, and so all the theorems end up being holding for any of these topological spaces, and there's a way to define continuous functions in them and all this that completely match what we think of continuity in the reals and complex numbers when we think of continuous functions. Okay, so let's see in the last few minutes, just to give you the notion of compact. This is a very important notion too. Okay. So what will be a compact set? Okay, a compact set is will be a set that has, essentially over the complex numbers and the reals will be a set that's both closed and bounded, right? So that there's no issues of sequences running away to infinity or approaching a point that are not in the set, right? So we want to, it's a set where essentially every sequence has at least a limit point or a subsequence that converges. Okay, but turns out that the right way to define compact is the following. We say that S is compact, and this will seem the first time you see it like a strange definition, right? So definition. Right, I have just a few minutes, so I'll just give the definition and we'll prove one theorem about it. Okay, definition: S is compact if and only if for any open covering of S. What do I mean by an open covering of S? I mean a set, right? Sets, say, let me use the letter O as in open, right? Sets O, say, let me use the letter X, sets OX open such that the union for all X in some space X of OX is equal to S, right? Or contains S. Maybe it's better to just say that it contains S. Okay, otherwise I have to talk about open in the relative topology, right? So you cover the set S with open sets. Okay, if for any open covering of S there exists a finite subcovering. Okay. So this is, it feels like a very strange definition, right? So for any way that I can cover a set with open sets, even if there's many, many, many of them, there's always a finite subcovering that works. Okay, so a theorem, which I will not prove. So over the reals, so over reals and complex numbers and so on, compact sets is equivalent to being closed and bounded. Okay, and this is, one of the implications is easy, the other not so easy, but also not so hard. Okay, but let me show a theorem that will highlight why such a definition makes sense and is actually extremely useful. Right? You could just say, if you're only interested in R and C, you could just say, closed and bounded. But actually, this definition will be very, very nice to use, right? And you can use it then over any topological space. So here's the theorem. So if S is compact, so let's call it a theorem, which I think is a great example of the importance of compactness and of the type of arguments that arises. Right? If S is compact, then every sequence in S has a limit point, or an accumulation point. Maybe I should use the word accumulation as an accumulation point. Right? Or another way to say this is it has a convergence subsequence. Okay, so I have 1 minute. Let me see if I can prove this in a minute, because this is super. This is a super, super nice argument. Okay, proof. Okay, let's say xn, n1 to infinity, has no limit point, has no accumulation. By a limit point, I don't mean necessarily the limit. I mean where you have a subsequence that has a limit, has no limit point or accumulation point. Okay. Okay. Then take y in S. Any y. Okay. Y is not an accumulation point of xn. Right? So what this means, well, it means that there exists some epsilon, right, for which b y epsilon, right, cannot, it needs to be that that by epsilon will, right? If it's not an accumulation point, it must be that by epsilon contains only a finite number of sequence elements, right? There exists such that by epsilon contains only a finite number of elements of Xn, right? Because otherwise, if for all epsilon you always had an infinitely many values of Xn, then it would be an accumulation point. Okay, so now let me, to make this easier to write, let me index this on epsilon of y, right? And this is definitely an open set. So b y epsilon y, right? If I take this set of these open sets for all y in S is an open covering. Right? Because every single point in S is in one of these open sets. In particular, for every y in S, it is right? Any point y in S is in particular in the by epsilon y, right? So what I did is I covered the set S with a bunch of open sets, all of which only have a finite number of sequence points. Okay? But now, because S is compact, right, I know that there must be a finite subcovering, right? So, okay, so if S is compact, let me go here. If S is compact, there must be a finite subcovering. But what does that mean? That means that I can cover S with a finite number of open sets, of which each one only has a finite number of Xn's. Right? So what would this imply? This implies that there's only finitely many points in Xn, but it's an infinite sequence, so that's not right. Right? So it's a contradiction. Right? And so this I think is it's a simple argument, but it highlights very nicely the importance of this definition of compact. And compact sets will be important because basically in a compact set, say over the reals, you always have a maximum, you always have a minimum. So it'll be a very natural place to define functions as well, right? Because they'll in general contain maximums and minimums when at least some, like its norm or something like real valued about it. Okay, sorry for taking a few extra minutes, but I just wanted to show this argument. So we go back to functions next Tuesday. All I tried to do is give you 2 examples of arguments in point set topology, just to sort of recall this type of arguments. And if you haven't seen them before, please go read a few of these arguments, or just read those pages of alphas, for example, just to get a sense of how these types of arguments go. Okay, but now we're going to go back to complex numbers, complex functions, and we're going to make use of connectedness and compactness, but in particular to the complex numbers. Okay, thanks so much, and sorry again for taking a few extra minutes. And I'm around, I can answer any questions, and I'll try to look at the chat now. Okay.